Which column is most likely to buckle? A pin connection on both ends, and this little signal here means it's a pin connection. So you can picture it like a rod being held between your fingers. That's a pin connection. You can kind of pivot. A moment connection on one end and free or no connection on the top. A moment connection on both ends, and a moment connection would be more like a rod being held in your fist. Go ahead and hit pause. The answer is this one, the moment connection on one end and free no connection on the other. So this is a little bit counterintuitive, but there are different ways to brace a column. And we have pin connections, we have moment connections, we have free connections, which are a little bit more unusual, and we have ones that are allowed to translate right to left, and we'll get to those. So if a column is going to buckle, we need to figure out not only the strength of the column and the length of the column, but the type of connection at the top and the bottom is going to kind of govern its likelihood of buckling. Now we're looking at a table, and here you have just different flavors of column. So in A, you have a fixed up, top, and bottom. On B, you have a pin connection at the top and fixed at the bottom. On C, you have something that's a rotation fixed but translation free on the top, and something that's rotation and translation fixed on the bottom. On D, we have two pin connections. On E, you have something that's fixed on the bottom and allowed to kind of move around at the top. And then on F, we have something that has a pin connection on the bottom and translation on the top. Now, what we're going to need to do when we do the calculation, when we kind of figure out likelihood of buckling, we're going to have to run through a formula, and I'm not going to get into the formula right here, but in that formula, there's a value of what's called K. And that K value, you look up on this table to determine its likelihood of buckling. And a higher K value means a higher likelihood of buckling, because in the formula, you're going to take the length of the column and you're going to multiply it by K. So in this one right here, we're going to take the length of the column and we're going to multiply it by 1/2. We're going to multiply it by 0.5. That means from a buckling point of view, this column of, say, 10 feet will behave more like a column that's only 5 feet. If we look at this one here, if we have a column that's fixed on the bottom and it has a pin connection on the top and it's 10 feet long, in terms of its likelihood of buckling, we're going to multiply it by 0.7, so a 10-foot column will look more like a 7-foot column when we size it for buckling. And then this is kind of our baseline. We have pin connections at the top and the bottom, which means that it's rotation-free and translation fixed. And that's our 1. So then if we have a 10-foot column, it's going to really behave like a 10-foot column. But look at these two here. These two have a theoretical K value of 2, which means that we're going to have to take a 10-foot column if we have one of these, and it's going to behave like a 20-foot column. So we're going to multiply it by 2. Now, right below that theoretical K value, there's another line that says recommended design value when ideal conditions are approximated. And that basically means we're talking about wood. So the theoretical K value can pretty much work if we're talking about something like steel that's pretty consistent, maybe even concrete that's pretty consistent, but wood is kind of weird. It's got knots and it's got wanes and checks and cups, and no piece of wood is perfect. No two are the same. So in this case, we're actually, in some of these situations, we're going to have a slightly larger recommended K value for wood. So let's go through examples of what we mean by rotation fixed and translation fixed and so forth. So this is a moment connection. We saw this before when we talked about steel. You know it's a moment connection because we've engaged the flange and the web, and we're holding both of them in place. And so that would be a rotation fixed and translation fixed. It's not going to slide up and down. It's not going to rotate. This is what we called a shear connection before. This one is what we would, in the language of that chart we just looked at, that table we just looked at, we would call this rotation free and translation fixed. It's not able to slide up and down, but even though there are 3 bolts there, it is actually able to kind of pivot because at the scale of the building, those 3 bolts are really kind of like a pin. Then we have rotation fixed and translation free. Go ahead and hit pause and try to determine where we use that kind of connection. It's in seismic. So remember we talked about buildings kind of sliding back and forth. And you'll note that we talked about structures in all kinds of other places, right? We talked about it certainly in steel, but in other places as well. So these are the seismic isolations that are in this case, under the Utah State Capitol. If we want something to be able to slide back and forth, that's going to be something we're going to call rotation fixed and translation free. So it can't pivot, but it can translate right to left. Finally, we have our rotation free and translation free. And certainly, of course, a flagpole comes to mind. You know what kind of works with this at this level? It's kind of rare, and it's not very common in buildings. We sometimes will see it if we have like a single column for a highway overpass. That may behave like something that is rotation-free and translation-free. Now, I just gave a in-person seminar at AIA New York, and one of the participants in that seminar asked, what about a really tall, slender building? Would that kind of behave at the scale of the building? If you were worried about buckling for the building, would that kind of behave in this way like a flagpole? And the answer is kind of yes. But in practice, the buckling would not be the biggest issue. In other words, you'd be much more concerned about other things. So the buckling for a tall building, first of all, buildings aren't quite that tall and slender like a flagpole. And secondly, there would be other factors for the building that would require beefier structure, and it would be unlikely that buckling would control. But yes, same principle.